This is your presenter Asloob Mudassar, and I am presenting slide number 82 of the course on laser physics. Question is, what are passive optical resonators? Discuss some important optical resonators. The answer is, in passive optical resonators, no active medium is present. In most lasers, the dimensions of the resonators is much larger than the wavelength of laser light, and the resonators are usually open, that is, have no lateral surfaces. The dimensions of the resonators are enhanced for greater gain. In closed resonators, the number of longitudinal modes is much greater in comparison with the number of modes in the corresponding open resonators. Waves which travel nearly parallel to the resonator axis contribute significantly to laser oscillations. Due to diffraction of waves by the resonator and optics, some optical energy leaks out of the open resonator cavity. The remaining energy oscillates back and forth between the resonator optics, forming a standing waves pattern with the electric field vanishing at the resonator optics. Standing waves form different modes of electromagnetic waves in the resonator. Such an electric field can be written as electric field E at the position R and time t is equal to, so this is the electric field that we are writing inside a resonator. So E at a position R and time t is equal to E naught, which is the magnitude of the electric field, multiplied by U of R, which is the spatial part of the electric field, multiplied by the phase factor e to the power iota omega t minus t over 2 tau c. So this is what we have generally written, an electric field value inside a resonator at a position R and at time t, where tau c is regarded as the cavity photon decay time. It is the time in which the mode intensity falls to 1 over E of its maximum value. So you see that here we are talking about mode intensity. In a resonator, there could be many modes oscillating within the cavity, as you will see later in this lecture. So if a mode is oscillating, then the photon corresponding to those modes will decay when the intensity corresponding to that mode falls to 1 over E of its maximum value. Now what is 1 over E? For this one you need to have a look at slide number 81, that is in the previous lecture. So here we are going to discuss some important resonators which are described below. First we discuss plane parallel resonator, which is also known as the Fabry-Perot resonator, in which two plane waves propagate along the cavity axis in opposite directions, forming modes of standing waves satisfying the condition capital L is equal to n into lambda by 2, where capital L is the length of the resonator. So let me show you first the figure. This is a plane parallel resonator. You can see that there are two plane mirrors at the end, at each end, and I have also shown plane wave fronts inside this resonator, and one plane wave which is on the left one has been shown to move towards the right, and the one on the right hand side is shown to move towards the left. So these two plane waves are moving in opposite directions, thus forming standing waves within the two plane mirrors. And at these two mirrors, the electric field due to these standing waves will vanish out. That is, the nodes of the electric field will the nodes of the standing waves will exist at the two plane mirrors. Under that condition, which is the length of the cavity is capital L, and under that condition the standing waves fit into this cavity is given by this relationship, that is L is equal to n into lambda by 2. Here we are saying that only one wavelength lambda is satisfying the condition for some value of n where n is a positive integer. But you see that if you choose this lambda instead of another lambda, then of course the number n will also be modified. So you see that different modes can fit, that is different value of lambda and different value of n can satisfy this condition. But you know that n is an integer, but there is no condition on the lambda that lambda has to be an integer. So lambda could be any value, but n has to be an integer. So you see that many wavelengths can satisfy this condition depending upon different values of n. So when different lambda can satisfy, it means that we say that different longitudinal modes are possible within the length L of the cavity, where n is a positive integer and capital L is the length of the cavity. Let's divide both sides of this equation by c. So we have L over c is equal to n by 2 into lambda over c. Now lambda over c can be written as 1 over nu, where nu is the frequency corresponding to wavelength lambda, and nu is the frequency of the longitudinal oscillation that will oscillate within the cavity, the wavelength of which one will satisfy this condition. So we can write down this equation as 2 over n into nu is equal to c over L. So this is a rearrangement of the variables. Or you can solve this equation for the value of nu. So nu is equal to n times c over 2L, and you can put a subscript n over here. So nu n is equal to n times c over 2L. So you see that this is the frequency n corresponding to the nth mode of the oscillator of the longitudinal mode, which satisfies this condition. So you see that in this condition you will notice that c is constant, which is a fixed number. 2L is also a fixed number. So for all positive values of n, you can have different frequencies that will satisfy the wavelength of which one will satisfy this condition, that is L times is equal to n into lambda by 2. So you see that here it is obvious in equation number 2 that different n can give you different values of new frequency, different values of frequencies, that is nu 1, nu 2, nu 3, depending upon n1, depending upon the value of n to be equal to 1, 2, 3 and so on. So you can satisfy different values of n over here, and you can get corresponding frequencies because the rest of the values are fixed. The frequency difference between two consecutive oscillating modes, the delta nu, is calculated as delta nu is equal to the frequency at nu plus 1 minus the frequency nu at value nu is equal to, so if you substitute these two values from equation number 2 from here insert over here, you will get that one equal to c over 2L. So the delta, which is the frequency difference between two consecutive frequency modes, is equal to c over 2L, which is constant, depends upon the velocity of light and also depends upon the length of the cavity. So if you change the length of the cavity, you can have different delta nu, that is different separation between the modes. But if the wavelength is, if the length is of the cavity is fixed, then of course delta nu will also be fixed. But you know that when your laser is operating, what will happen? The length of the cavity may change due to thermal variations. That is, the temperature of the cavity may rise, and of course due to that one the length of the cavity may change, and due to a slight, very small change in the length of the cavity, then of course a small change can also be noticed in the value of delta nu. These oscillating modes are also known as longitudinal modes of oscillation. So you see that again I am talking about this time, the second times about the longitudinal modes. So these nu n are the nu n given by equation number 2 gives you the longitudinal modes, or equivalently equation number L is equal to n times lambda by 2, where you can have different wavelength to satisfy this condition. So different wavelength mean different longitudinal modes, or different frequencies mean different longitudinal modes. Next we consider the concentric resonator, which consists of two identical spherical mirrors, each of a radius of curvature capital R, and separated by a distance capital L is equal to 2 times capital R, with their center of curvatures coincident at a common center called capital C. So you will see, you will notice in this diagram that you have two spherical mirrors on each side of the cavity, and I have shown two spherical wavefronts shown in dotted in between the two spherical mirrors. So these are the two spherical wavefronts. So these two spherical wavefronts will converge at the point C and then will expand on the other side. So for example, the left one will travel, it will converge at point C and will further travel as a diverging spherical wavefront towards the spherical mirror on the right hand side, and similarly for the other spherical wavefront which is on the right hand side of this one, that will move towards the point center C towards the left, and then it will diverge in the form of a spherical wavefront as shown on the right, as shown on the left of the point C. So point C is the center, which is a common center of curvature for these two spherical mirrors, and you know that L is actually the separation between the two spherical mirrors. So this geometry is called the concentric resonator. Spherical waves originate from the common center of curvature and travel in opposite directions. The resonant frequency or the modes frequency is given by. So you see that the modes or the resonant frequencies in this oscillator, in this cavity, in this resonator is given by nu is equal to n times C over L. You can also put a subscript at the frequency nu, that as we have used a subscript n with the frequency nu in equation number 2. Similarly, actually this is the same equation as equation number 2. So you can also use a subscript with the frequency nu as well. So nu is equal to n times C over 2L. So you can see that with the different values of n, different modes can exist within the concentric resonator. And the difference in the frequency between the two consecutive longitudinal modes is given by delta nu is equal to C over 2L. This is the same as we have found previously for the case of a plane parallel cavity. For the case of a cavity having two mirrors parallel to each other, and is called plane parallel resonator. So you see that delta nu is the same in the case of concentric resonator as in case of the plane parallel resonator, which is equal to C over 2L. The concentric resonator, you know, that is shown in figure number 82.2, which I have just explained. So you see that here you should notice that L should satisfy the equation that L, capital L is equal to 2 times R, because the C is a common center of curvature for the two spherical surfaces, and each spherical surface has a radius capital R. So the separation between the two spherical mirrors is 2R, which is equal to capital L. So L is equal to 2R. Third resonator is the confocal resonator, which consists of two identical spherical mirrors, each of radius of curvature equal to capital R. So the story is the same as the previous one, but now they are separated by a distance capital L is equal to R. In the previous one, for example, in this case, the separation was L is equal to 2R. Now here in the case of confocal resonator, the separation is L is equal to capital R. That is, the center of curvature C1 of mirror 1 is centered on the second mirror, and the center of curvature C2 of the second mirror is centered on the first mirror. The confocal resonator is shown in figure number 3. You can see that we have spherical mirror 1. On the left, we have spherical mirror 2 on the right hand side, and the center of spherical mirror 2, which is C2, is lying on the spherical mirror 1, and similarly the center of curvature of the spherical mirror 1 is lying on the spherical mirror 2. So you can see you can notice the position of C1 and C2, which is the center of curvatures of the spherical mirror 1 and the spherical mirror 2, lying on the opposite mirrors respectively. So you see that you can also notice the ray diagram over here, that the rays can travel parallel to the optical axis or parallel to the resonator axis, as well as it can make any other angle with the resonator axis. The waves within the resonator are neither plane nor spherical. So you see that here this is very important point about the confocal resonators, that we cannot specifically identify that the wave fronts within these two spherical mirrors of the confocal resonators they are neither plane nor spherical. The mode frequencies cannot be obtained simply from the geometrical considerations of the cavity alone. That is, we cannot associate the longitudinal modes with the length L in this specific case, in case of confocal resonator. The next resonator is the generalized spherical resonator. In this resonator, two identical spherical mirrors of equal radius of curvature capital R can take any separation L. So you see that here in the previous two cases, for example, in case of the concentric resonator, we have the separation between the two mirrors satisfying the condition that capital L is equal to 2 times capital R. And in case of confocal resonator, the cavity resonator satisfies the condition that capital L is equal to R. But you see that here we have again the two in the generalized spherical resonators, we have the two spherical mirrors, each of a radius of curvature equal to capital R, but now they can be at any separation capital L, such that L could be greater than capital R and is less than 2 times R. A ray will not repeat its path even after many passes. So you see that if you form such a cavity, the array will not follow its previous path if after many repetitions of the oscillations between the two mirrors. So the ray will not trace itself back after many oscillations. Here I have shown a typical diagram which contains a plane mirror on the left hand side and a spherical mirror on the right hand side. This resonator is called unstable resonator. You will notice that a ray in the center shown with an arrow is traveling parallel to the resonator axis. Then of course the spherical mirror is trying to push it outside the cavity, outside the resonator. So it is reflected at some angle. And then you see that the plane mirror will follow the angle of incidence is equal to angle of reflection will be followed at the plane mirror. So ultimately after maybe I have shown over here that after two reflections the ray will go out of the cavity. But you see that in reality the angle, since this ray which is parallel to the resonator axis is making a very small angle with the resonator axis, so it will take multiple oscillations between the two mirrors before it exits the resonator. The mirrors could either be convex with capital R less than 0 or concave with capital R greater than 0. These are the sign conventions that we use with the convex and the concave surfaces. The resonator can either be stable or unstable. In unstable configuration, a ray diverges away from the cavity axis during multiple passes and finally leaves the cavity. An unstable resonator is shown in figure number 4. And you see that this is what I have explained about this unstable resonator. Now the ring resonator is the type of resonator in which rays are arranged in the form of a ring. For example, over here you can see that it forms a ring, a triangle formation, in which rays are arranged in the form of a ring. A simple triangular ring resonator and a bit complex folded ring resonator are shown in figure 5. So this is a ring resonator on the left, containing optical diode in one of its arc, and the oscillations are taking place in the clockwise direction. And on the right hand side we have a folded ring resonator. This geometry on the right hand side is referred to as the folded ring resonator. And you see that it contains 4 mirrors. but in the left one we have the 3 mirrors. And in the resonator on the right hand side, the rays can travel both directions, that is both in the clockwise direction and in the anti-clockwise direction. And the caption is simple ring resonator on the left, folding ring resonator on the right. The total phase shift along the ring path in both geometries must be an integral number of 2 pi, that is phi. Phi is the phase that the light will undergo in one pass. Phi is equal to k times Lp. K is the wave number, Lp is actually, this is what we have defined Lp over here. Lp is the length of the ring perimeter. So the whole geometrical distance in one ring is actually Lp. So Lp is the geometrical distance that the light will travel in one pass. So k times Lp, this must satisfy the condition, is equal to n times 2 pi. For the oscillations, for the stability or for the oscillations to take place in these two oscillators, in these two resonators. So we can simplify this one. We can insert the value of k, which is 2 pi over lambda, and then we have Lp, and the same condition is equal to n times 2 pi. And we can solve it for 1 over lambda, which is equal to n over Lp, because the 2 pi will cancel out from both sides, and then we can multiply c on both sides of this one. So we have c over lambda is equal to nc over Lp. C over lambda can be used as nu. So we can write in terms of the frequency nu, that nu is equal to nc over Lp. So you see that c is constant, Lp is also constant for a ring resonator, and you see that n is the number. So using different value of n, you can set up different modes in the cavity. So where Lp is the length of the ring perimeter and n is again a positive integer. So it means that you can set up different frequencies or different longitudinal modes in the cavity by choosing different values of n, or ultimately different values of n will be satisfied, and so you can get different modes. So in the same cavity, many frequencies could be possible, because you can insert different values of n and you can obtain different frequencies, that is different longitudinal modes. So in one ring laser, n could be take different values, so nu could be different values. It means that different frequencies can exist even in a ring laser. It means that different longitudinal modes are present in each of these ring resonators, and these are called longitudinal oscillations or longitudinal modes. Light travels both ways in the second geometry and forms standing waves, whereas only clockwise propagation is possible in the first geometry due to the presence of the optical diode. Thus the concept of cavity mode and cavity resonance frequency is not confined to standing wave formation within the optical resonator. Both stable and unstable configurations are possible with ring cavities. So you see that here in this lecture we have described different types of resonators which are commonly used as passive resonators for lasers, and we have described them. We have also described the conditions for the occurrence of the longitudinal modes in each of these cavities. So this is the end of slide number 82.